This topic of linear momentum comes from the work of Isaac Newton. Isaac Newton wrote his book, The Principia Mathematica, in 1687. And of course, out of this book came his three laws of motion. The first one being definition of inertia and equilibrium. The second being what people usually think is F equals ma. We're going to do it as sum of forces is equal to ddt of k. Now k is this new topic, linear momentum. So we're going to come back to equation 2 in just a moment. And of course his third law is action and reaction. Now, when Isaac Newton wrote his book, he was using this equation, his second law, to solve problems of the motion of planetary bodies in elliptical orbits. And when he did, he was modeling his planets not as bodies with a volume, but instead he would model the planets as particles. And of course, we've talked a little bit about particles. You take some actual body with volume and you condense it down into a single point. So Newton showed that his second law does work for particles. The sum of forces on this particle, you could have a whole series of forces acting on it. The summation of those forces is going to equal the change in the linear momentum of that object. Now, what is the linear momentum? Well, linear momentum is mass times velocity. Now, in most cases, the mass is going to be constant, or for example, the object is going to stay together, right? We know that mass doesn't actually ever be created or destroyed, except in cases with weird transfers between mass and energy. But there are cases where your object can be ejecting mass, for example, like a rocket, satellite, for example. And there are cases where mass actually comes together. So that's called, when you're ejecting mass, it's called ablation. When mass comes together, that would be accretion. You see accretion in cosmic events, in the formation of stars and planets. Now, in most cases, this is going to simplify down to mass times acceleration. We are, however, going to have one video. There is going to be a video on rockets. So we're going to do some fun derivation of rocket equations. And if you want to do that kind of work, then you do not say F equals ma. You don't jump to the end because you're going to miss some very important details. All right. So what we want to do in today's video is we want to take Newton's second law and we want to say, okay, it works for particles, but does it also work for bodies with actual volume, for continuous bodies, bodies with distributed mass? Now, in order to do that, we have to introduce a new character into this play, and that character is a man named Euler, Leonhard Euler. So about 50 years go by after Newton produces his work, and this guy Euler comes back and he takes Newton's second law and he proves that it can be used for objects with volume. And that becomes Euler's first law. In addition to that, Euler also shows how this law, starting with this law, you can then derive another equivalent law, not for translations, but now for rotations. So instead of forces, we're going to be looking at moments, and instead of linear momentum, we'll be looking at angular momentum. So that's going to be in a separate video. So what we want to do today is we want to take Newton's second law and we want to turn it into Euler's first law. So is this law for particles also applicable for bodies with volume, continuous bodies? I'll tell you the answer, yes. Yes, it is. So what we need to do is we actually need to, we're not going to start with equation 2. We're going to come back to it in a few minutes. What we need to do first is we actually have to have a discussion about center of mass, what it is, how you find it, because from that discussion we actually get some important points that we're going to carry into this derivation. So let's get started. Here's a rigid body. Let's call it body A. On body A is a known center of mass, point A. We can take body A, and if we wanted, we could divide it up into subspaces, and we could say, here is some little differential bit of mass, and let's call the point, right? Let's call the point where that mass is located point B. Now, there could be 1,000 points that we break it into. There could be 10,000. There could be 10 million, right? We can break this volume into infinitely many tiny little differential bits. So let's call this b sub I, in that we could iterate over all of these little differential bits of mass. If I want to know where the center of mass of this body is, and of course we're going to put this in, with respect to some point, we would put a body frame on this and we could define it in some inertial frame. If we want to know where the center of mass of that point is, here's how we're going to find it. The location of the center of mass, consider that that is going to be the position vector from N to A. Now, the definition of center of mass is, it is the weighted average of all of the position vectors of all of these little differential bits of mass. So here's what I mean. First thing we're going to do is we're going to sum all of the position vectors. So the position vector from N to B sub I, we're going to perform a summation over all of these, all of the little differential bits, and we're going to take the position vector, right, all of them with respect to point N, and we're going to multiply those by the mass of those differential bits. And then once we have this summation, then we're going to normalize it by the total mass of the body. Quick comment, we could, instead of doing this as a discrete summation, we could also approach this problem as a continuous problem, and we could solve this through integration. We could integrate over all of these position vectors with respect to a differential bit of mass. That's also possible. Some of the derivations we're going to do in the next couple of videos, we are going to do them continuously with integration. Some of them I'm going to do discretely. And the reasoning there is just because these videos are intended for an undergraduate course, and sometimes it just seems more intuitive to use the discrete. But also, just as a quick comment, what if you have a system where you have multiple rigid bodies? For example, here is a series of 3 blocks, block A and B and C, and each one of them has their own center of mass. Well, this equation above can actually be used to find the center of mass of a system of rigid bodies. You take the position vector of A and the position vector of B and the position vector of C, you multiply them by their own respective masses, you linearly add them together, and then you divide by the total mass, A plus B plus C. And that gives you the mass of the system, which could be, depending on where they are, maybe we call this capital G, right? Center of gravity for the whole system. So you would do the same thing, same equation as we're looking at above. All right. So what can we do with this equation? We'd like to massage it just a little bit and see if we can find something interesting. What we can do is we can take this position vector and we can redefine it. Consider that the position vector from N to point B sub I can be rewritten in this way. We could take the position vector from N to A, right? We can go from point N to point A, and then we can go from point A to point B sub I. What if we take this and we insert this definition into the equation above? Now, the position vector from N to A is, we're going to put our normalization term in front. I'm going to say, here's the infinite summation. And now let's bring in this position vector and replace the one above it. So P into A plus P ABI, and then that is going to be multiplied by this scalar mass of B sub I. Next, consider that we can take this plus sign and we can break this into 2 different terms, right? We can distribute this summation. So P into A is going to equal 1 over MA. Here is the first term. We're looking at P in A times MBI, and then plus. Here's the second summation. And now P ABI times MBI, and then close brackets. Okay. What can we do with this now? This is the exact same thing. We haven't added anything to it. We're just doing some redefinitions. Consider now this first piece, the position vector from N to point A. This position vector doesn't change, right? It has nothing to do with the infinite summation. It doesn't matter which B sub I we're looking at, right? The P and A is constant. That means I can pull it out of that infinite summation. So P in A, 1 over MA, and now this is P in A times the infinite summation of our little differential bit of mass, MBI, plus infinite summation of P ABI MBI. Now, what does this tell us? This piece right here, what is that? Well, we're literally saying take all of the differential masses, MBIs, and sum them all together. If you do that, if you take this mass and that mass and that mass and that mass and you add them all up, you get the mass of the whole thing. So P into A is going to equal 1 over MA times, this is P in A, and this is MA, plus this remaining term now, infinite summation of P AB sub I MBI. All right, so what's going to happen? Well, clearly we can distribute the 1 over MA to both of these. And if we do that, this first term is just going to become PNA. PNA, there we go. And then plus, and of course over here we've got, we can drop the brackets now, and I can divide this one by MA. So it's very clear what this means then. And of course we could multiply through by the MA again just to make it a little more obvious. But the point of all of this is that this piece of the derivation now, this part, this summation, this is equal to 0. And this is a very important claim, that all of the different masses around the center of mass, they all cancel out, right? If you do this weighted average, this component is equal to 0. Now, this may seem intuitive or it may seem simple. You may be wondering, what's the point? My advice is to take this and put it in your notes and keep it, because as we go through some derivations, not just the ones today, but several derivations in the next few videos, this term actually continues to crop up as you expand terms, as you do redefinitions, right? We can work through the derivations and this will continue to crop up. And knowing that it's equal to 0 means that we can start letting those terms equal 0, right? They're going to drop out of the derivation and it's going to make the whole process simpler. So this is really what we needed out of this discussion on center of mass. So we have this. Next, let me clean this up, and now we're going to start going after Newton's second law and see what we can do with it. Let's start by laying out Newton's second law again. Sum of forces, in this case we're talking about the sum of forces on body A. So I'm going to say the sum of forces on body A, and this is equal to ddt of Ka. And as we said before, K, linear momentum, is mass times velocity. So mass of A times velocity of A. Now, some claims about this sum of forces. You can have forces acting at all kinds of points on your rigid body. You can also have multiple forces acting at same points or different points. For example, we could have several forces acting at this MBI. We could have forces acting at a point up here. We could have more forces acting at another point. We know that gravity is going to act at the center of mass, etc. So what's another way that we could write this sum of forces on A? We can say that the sum of forces on A, this is also equal to this. What if we do all of the forces acting on these little differential bits of mass? So we have some differential point, right? Differential mass at point B sub I. And I'm saying if you sum the forces on that little bit of points, and you sum all of the points, right? That gives you the sum of forces on the whole body. And of course, we can arrange these summations in any order we like. They're reversible. So, what about this right-hand side? Well, this right-hand side, we could actually write a Newton's second law for just this piece, right? So what I'm going to do is I'm going to take, we know that the sum of forces on A is equal to this, ddt of MA VA. And then I'm going to take this guy and I'm going to rewrite this. So this is ddt of, we still have this infinite summation, and this is now M BI V BI. All right, how does this help? What are we going to do next? Well, what we would like to do is we'd like to work with this infinite summation a little bit. There's not a whole lot we can do about MBI, but we could actually redefine VBI using transport theorem. This is why in the order of this class, we teach you transport theorem before we dive into these topics. So how could you redefine the velocity of point BI using transport theorem? Consider that we know what the definition of this is. This is the derivative of P into BI. And as we did earlier, we know that this is P into A plus P ABI. Now, if we were to distribute the DDT to these two, this first term, this is going to be VA, and the next term is going to be VA to BI, right? So we're going to have the, and it's plus. We're going to have the velocity of A plus some relative velocity. Now, this is generalized, right? We don't have a literal position vector to this point because there's infinitely many points. And we're, right, sorry, the summation's here. I thought I left it out. There's the infinite summation over all of these points. Okay, so what we want to do is we want to rewrite this using transport theorem, and we're going to leave it general. So VBI then is VA plus omega n. Now remember, with transport theorem, it's whatever frame you're taking the derivative of. This is rigid body A. All of the position vectors would be in frame A. So omega into A. It's omega into A cross P ABI. Again, we're going to leave it general, right? Every different point B sub I is going to have a different position vector. Next, let's take this definition of velocity and let's put it inside of this equation. So here's what we're going to have. Notice, for example, before we do that, before we insert, I'm going to combine some steps. Consider that we could take the integral of both of these sides, right? Both sides of the equation. And if we do integrate both sides of the equation, we're going to lose the derivative with respect to time. And here's what I mean. Integrate both sides of these with respect to time. So multiply dt. dt, of course, will cancel with this. You're left with just the d operator in front of each of them. And then we integrate them. And those derivative terms are gone. So what we're going to be left with is MA VA, right? Because the DDTs have dropped. And then the left-hand side is going to be infinite summation of, now this is just VBI, but it's VBI multiplied by the scalar mass. So I'm going to write it as VA times MBI plus omega NA cross MBI P ABI. Now there's a particular reason I wrote it that way. One, it's convenient, and it's gonna let us just walk right up to the answer. But what I've done is I've distributed the MBI, right? And also MBI is a scalar, which means you can move it throughout these equations, okay? And then the summation's on the outside. So what are we going to do next? Well, looking at this equation, consider we could also distribute the infinite summation. It's the infinite summation of this first term plus the infinite summation of the second term. If we look, if we focus just on the first term, consider that VA is constant with respect to this infinite summation, right? The velocity of point A is whatever it is, and it doesn't matter which B sub I we're looking at. So we can rewrite this again. We can say that MA VA is equal to, I'm going to pull the VA out of the summation. This is VA multiplied by the infinite summation of MBI plus, and then here's the second term. Infinite summation of omega NA cross MBI PABI. Now, we can actually do the same thing on the second term as well. Consider that omega NA is also constant with respect to the summation. Every one of these little points, B sub i's, they're all on body A, right? But omega into A describes the rotation of the A frame, which is attached to body A, and it doesn't matter which of these points we're focused on. So let's rewrite this second one as well. And when we do that, we're going to pull out the omega NA cross. And then here is the infinite summation. All right. So what are we going to do with this equation? Well, the left-hand side, I'm going to go ahead and I'm going to write that as Ka. We know that MAVA is linear momentum, K sub A. The first term, the infinite summation of all the little B sub I masses, well, that's just MA. So we have MAVA, this next term, plus omega NA cross, and just to make it really obvious, this is PABI times MBI. I think that's how we had it written a moment ago. Maybe not, maybe we had it written this way. Regardless, this is that piece that we had from the previous derivation, the discussion on center of mass, right? And in that discussion, we said that this is equal to 0. So when this is equal to 0, what does that mean? That means Ka is equal to MAVA. Well, that seems really obvious, right? What was the point? What did we just do? What we just did is we took Newton's second law, which is originally for particles, and we said instead of a particle, now we have a body with volume, right? And if you have a body with volume, and you know where the center of mass is, it turns out that Newton's second law still applies, right? The linear momentum is now the mass of it multiplied by the velocity of the center of mass. So even for bodies with volume, distributed mass, we can still make this same claim. We can say that the sum of forces on body A, this is going to be equal to dt of the mass of A times the velocity of A. Now this, specifically in the case of continuous bodies, this is called Euler's first law. So, what do problems with linear momentum look like? You have a homework in which you have to answer questions about linear momentum of bodies and linear momentum of systems. Suppose that we don't have just one general body. Suppose that we have a whole series of bodies. Suppose that we are looking at some kind of mechanism. We'll go back to our old friend, the 4-bar linkage. Now, we can answer questions about the momentum of the whole mechanism. Consider if this is point A, and this one is point B, and this one is point C. The questions that we can answer now, we could answer what is the linear momentum of A? What is the linear momentum of B? What is the linear momentum of C? What about the linear momentum of the whole system? Well, it turns out that you can actually just add all of these together. You can say that the linear momentum of the system is equal to the linear momentum of A plus the linear momentum of B plus the linear momentum of C. Now, where this claim comes from is, again, we mentioned it earlier, you can find the center of mass for the whole system. This system is going to have some center of mass, we can call it G. And if you want to find the angular momentum of the whole system, then the angular momentum of the whole system is the mass of the system, mass of G, multiplied by Vg. So what do we need to do to evaluate this? Well, the mass of the system is ma plus mb plus mc, and the velocity of the center of mass of the system is going to be ddt of p into g. Well, what was p into g? P into g was the weighted average of the masses of the whole thing. So this would be ddt of 1 over ma plus mb plus mc, right? Times p into A times ma plus p into b times mb plus p into c times mc. All right. And you can take these and you can combine them, right? If we take mg, which is this, and we multiply by this, clearly that's going to cancel here. And then what we're going to be left with, notice, is the ddt of p into A times ma, p into b times mb, p into c times mc. So this is, you take these two, you add them, multiply them together, and then you can very clearly show that the linear momentum of the whole system is just a linear combination of each of these linear momentums. All right, so the problems that you're going to have in your homework, I think one of them is a 4-bar linkage, one of them is a double pendulum, one of them is a crank slider, right? But consider, we could give you any problems for homework or an exam. I could ask you to come back and tell me what are the linear momentums of the bodies, what is the linear momentum of the system, and really, the only thing it requires of you is that you're able to construct some position vectors, right? And do the velocity of these points. Ka is going to be a function of Va, Kb is a function of Vb, and Kc is a function of Vc. So we've tested velocity, so now you just take those velocity terms and you multiply by the mass. And of course, velocity is a vector, so you multiply by a scalar mass, that means linear momentum is also a vector, which again is consistent with Newton's second law, Euler's first law, because sum of forces is ddt of k, and forces are also a vector. All right, so that's going to do it for this video. We're going to have some example videos where I'm going to give you a problem and we're going to go through and we're going to do linear momentum, angular momentum, energy, etc. But honestly, I expect that if you can do the kinematics, you can do the linear momentum as well. There's nothing overly tricky about it. Okay, so that's it for this video. We're going to do a whole series of videos talking about these ideas of momentum. The next videos coming up are going to be on angular momentum. So we're going to connect this idea of, well, we have forces and we have translation, but here's an open question. The open question from this discussion was this. On these bodies, right, when we broke it up and we said all these little differential bits, when we added all the forces up, we just did the summation. I summed all the forces on this, I summed all the forces on all of the b sub i's. But what about where those forces are? Does that affect the problem? Consider that a force acting at this point has different effects than a force acting at this point and a force acting at this point. What if the forces are going in the same direction, but they're just at different places now? So we could have this exact same force, and what if it was just attached to a different location on the body? Clearly the location on the body matters. So in the next video, we're going to begin with Euler's second law, and then we're going to ask the question, what about the location on the body? And we'll see what happens. And what comes out of that is the equations for the rotation of the body. All right, so that's it. Best of luck, and I will see you later.